All right, good morning, everybody. Yeah, we're going to do section 4 today, which is trigonometric substitutions. Trigonometric substitutions occur when we replace the variable of integration by a trig function. In other words, what we're going to do is we're going to take the Pythagorean theorem, the rules of sine, cosine, and tangent, the relationship with the triangle. We're going to convert those factors into trig functions, or conversely, from trig functions to those values. So we're going to use substitution of, for x will be a tangent, and if this stuff here doesn't make sense, for x is a sine tangent or sine theta, and x secant. If these don't make sense to you, what they are is, for example, here it's tangent. The rule of tangent, using SOHCAHTOA, tangent of theta equals opposite over adjacent. Or if we multiply both sides by the adjacent, we have opposite equals adjacent times tangent theta. And that's what this is all talking about here. So here's the adjacent. If here's your theta, the adjacent is here, the opposite is here, and then the square root of a squared plus, well, call it x squared, the square root of it, that's hypotenuse. All right, so this is how we're going to convert everything. So here's a conversion. With x equals a theta, we just looked at a plus what's inside the radical, a squared plus x squared is the same thing as a squared plus the x represents the x, which is opposite, the a tangent squared theta squared. So since they both have an a squared, they factor it out. We get 1 plus tangent squared. 1 plus tangent squared is the same thing as secant squared. So a squared plus c is the same thing as a squared secant squared. Conversely, we keep on going. If we had a for the sine value, we have opposite over hypotenuse, x over a. So this one would be a squared minus x squared. And we continue doing this, where 1 minus sine squared is cosine squared. And secant, same thing there. Now this one is x squared minus a squared. They both have a squared, so we have secant squared minus 1. Secant squared minus 1 is the same thing as tangent squared. It's all the identities that we have on your cheat sheet. Now, these also occur, all these values occur in certain subintervals, which we have to be very, very, very selective about. The x equals a tangent requires the inverse to exist, and it has to be within that domain. For the x equals a sine, it requires the theta equals the inverse of sine. So in order to be continuous, it has to have the inverse and inverse conversely. And then we'll have this domain. So these are the important, so we'll use these formulas to do our derivatives and integrals. The procedures we'll be using to solve these: write down the substitution for x, calculate the differential dx, and specify the selected values of theta for the substitution. Substitute the trigonometric expression with the calculated differential into the integrand, and then simplify it. All this stuff sounds pretty difficult, but it's actually really straightforward once we'll do the first example. integrate the trigonometric integral, keeping in mind the restrictions on the angle theta, because that's what we just had earlier on this page. We had where those can occur. And draw an appropriate reference triangle to reverse the substitution. So we'll look at all these. All right, so to begin with, let's look at example 1. Evaluate. So example 1 is evaluate this integral. What's going to help us here is trying to find which ones. So we have, this is a, so it's a squared plus x squared. So which one of these have a squared plus x squared? This one, the secant conversion. So set the differential, so we know not differential, but the substitution. Since it equals secant, this is our conversion. So x equals a tangent theta. A squared equals 4, so a equals 2. So it's 2 tangent theta. Okay, that comes from here. X equals a tangent theta. The differential of that, dx, leave the 2 alone. The derivative of tangent from your cheat sheet is, the derivative of tangent is secant squared d theta. And from our tangent, we have, our domain is going to be from negative pi over 2 to pi over 2. So we're just setting everything up right now because this thing has to be a squared plus x squared. So inside here, we have 4 plus x squared, which is equal to 4 plus x is 2 tangent theta squared. Which is equal to 4 and, well, let's just square both of those. We have 2 squared tangent squared, 4 plus 4. Tangent squared is the same thing as 1. Now we're going to do version. So we have, we'll do piece by piece. Tangent squared theta. They both have a 4, so we can factor out a 4. We have 1 plus tangent squared. It'd be much easier doing it that way. 1 plus tangent squared is secant squared theta. So the 4 plus x squared, we can rewrite it as 4 secant squared. So inside here, four plus x squared. Now this can be replaced with, we're not going to do thetas. So it's 4 secant squared theta. And dx on top. This dx was this. So on the top we have dx. So that becomes 2 secant squared theta d theta. This is the conversion because we're going from x to theta. And this is square root of 4 secant squared theta. Now, can secant theta from our domain ever be negative? Not really, because it's always going to be square. So our domain, we don't need the absolute value on the bottom. So typically, when we take the square root of a square, we put a absolute value, but we don't need to because it won't be negative in our domain. So this is square root of 4, square root of secant squared, which is 2 secant theta, because that could never be negative. So I don't have to put the absolute values. So that cancels. That cancels. So we have so far we're going from here to here. The integral of secant from our cheat sheet is the ln absolute value of secant theta plus tangent theta plus, since it's an indefinite integral, we have to put a plus c. So since we started off in algebraic terms, we have to go back to algebraic terms. So secant let me see, where is that? Well, up here, we know that tangent is x over 2. So this is x over 2. Now we're going to find out what secant is. So we know here, we know this and that. So we know that 4 plus x squared equals 4 secant squared theta. Divide by 4. And if we square root, so we'll have square root of 4 plus x squared over 2 is equal to secant theta. So secant theta is square root of 4 plus x squared over 2. And there we have it. So this is the integral of this function here by using a trig substitution to get there. All right, let's see. Right, so let's look at example 2. This one's not really an example, it's more of an explanation, but we'll work it through. Here we find the expression for for the inverse hyperbolic sine function in terms of the natural logarithms. Follow the same procedure in example 1. Okay, so we start off with that. So in example 2, we're saying here a squared plus x squared. And what we got from the first example is that. And our conversions were x a tangent theta, and our dx was a secant squared theta d theta. That's where we're going to start off with that. So our integral of secant, which we saw earlier also, is ln of secant theta plus tangent theta plus our constant. And secant, which we calculated, secant theta was the square root of 4, or a squared plus x squared over a. So secant is the square root of a squared plus x squared over a plus x over a. Let's do this. So we knew this is that, but the integrals, here we go. So out of all these, which one has the square root of a plus x squared? So that's the inverse of the hyperbolic sine. That's the same structure we have here, the square root of a number plus the variable squared. The other ones are minus this one, but it has an absolute value of a. So it has to be the inverse of u, inverse of sine of u. So that means we know that this, the inverse of sine of our function, which was x over a, is equal to this. Squared plus x squared over a plus x over a plus c. So let's see what happens. Set x equals 0. See what happens at the origin. What happened over here? We'll have ln a squared plus 0 squared over a, 0 over a plus c. A squared is a squared over a plus 0. A squared is a, so it's ln of absolute value of 1. So ln value of ln of 1 is 0. So our constant set this equals 0, c equals 0. So we know that our hyperbolic inverse of x over a is equal to this conversion without any constant. So this is the integral of is the same as all this. Where's my examples? Oh, there it is. Okay. Let us now look at example 3. X squared dx over 9 minus x squared. So we have the integral of x squared dx of 9 minus x squared. So what we'll look at is 1 over a squared minus x squared. Since a squared is 9, that means a is 3. Okay, just using our first page of our notes. There's so we have a squared minus x squared. A squared minus x squared. So we'll be using this formula. And then we'll go to that. So our x is equal to a sine theta, which is 3 sine theta. We have to find the derivative of that. The derivative of sine is cosine d theta. Again, the domain of this is going to be negative pi over 2 to pi over 2. Now let's look at our function here. We have 9 minus x squared. X is that. So we have 9 minus 3 sine theta squared. Which is 9 minus 9 sine squared theta. We can factor out the 9. Which is equal to 9 cosine squared. That's the identity. So in place of 9 minus x squared, we could put 9 cosine. So our function x squared dx 9 minus x squared can be written so this is 9 cosine squared theta x squared dx. Since x is equal to 3 sine theta, x squared is 9 sine squared theta times our dx. So it's 9 sine squared theta times our derivative, 3 cosine theta d theta. Again, we're switching doing the transformation, the substitution into trigonometrics, so we have to go from x to theta. All right. So on top we have 9 sine squared theta times 3 cosine theta. On the bottom, it's going to be 3 cosine theta. So the 3 cosine thetas cancel out. That leaves us only with integral of 9 sine squared theta d theta. Here, we're running out of space. So 9's a constant, it can go out front. Sine squared theta is the same thing as 1 minus cosine 2 theta over 2. The reason we're going to do that is because we want to drop down from an exponent. If we could put 1 minus cosine squared theta, but we still have a squared term. We want to do a step down process, because now it's much easier just to do this function. Okay, that's a constant, so it goes out in front. So we have 1 minus cosine 2 theta d theta. We can do those in pieces, in parts. So the integral of 1 is theta, because we're doing d theta, minus the integral of cosine is sine 2 theta, and we needed a 2 in front, plus our constant. Okay, so we distribute that. From our cheat sheet, sine 2 theta is the same thing. Is 2 sine theta cosine theta over 2 plus c. Okay, so as far as we can go there, now we got to put it back in terms of x. So we went as far as we can here. So let me write that down. So it's 9 over 2 theta minus 2 sine theta cosine theta those cancel. So just sine, those cancel. So it's just sine cosine. All right, so what we have up here, sine theta is x over 3. We have 9 over 2. We'll get to this one in a second. Theta. Sine is x over 3 times cosine theta. We'll preserve more. Okay, what's cosine? When we find cosine from this. So 9 minus x squared equals 9 cosine squared theta. Divide by 9. So cosine squared theta is 9 minus x squared over 9 square root. Cosine is 9 minus x squared over 3. That's what cosine is. So in place of cosine, we have x over 3, square root of 9 minus x squared over 3. Yeah. Now we got to figure out what theta is. From that, since we have sine is equal to x over 3, since sine theta equals x over 3, if we take the inverse of sine of both sides, so we have theta equals inverse of sine of x over 3. That's what theta is. Inverse of sine of x over 3 minus x 9 minus x squared over 9. Now we can distribute. We have 9 times inverse of sine of x over 3 divided by 2. The 9's cancel, so it's just x 9 minus x squared over 2 plus c. And there is our integral of, what was that function? X squared dx over 9 minus x squared. So it's a process of simple transformations as we go along. Well, I don't want to say simple. It's just that there's a lot of pieces, like a big puzzle. And again, use your trig cheat sheet for all these identities, because we always want to go down from a power, because we can't. It's difficult to integrate with cosine squared or sine squared. So if we make it go down to a lower power, then it's a lot easier. And our last one, example 4. Find this one. 25x squared minus 4, where x is greater than 2/5. This is important because if not, then the denominator will be, if it's equal to 2/5, it'll be 0, and if it's less than 2/5, it'll be negative. So it's got, our domain has to be larger than 2/5. All right, let's look at our formula sheet. Want the integrals. There's nothing that has an AX or AU. So it'll have to be one of these two down here because we need to factor something out. We have to get rid of that coefficient there. So let's look at the denominator. We have 25x squared minus 4. That's the same thing. Let's get rid of this one. So we have to take it outside. Take it outside. This one needs it. So it needs a 5 squared over 5 squared. But since I took that out, this is x squared minus 2 squared over 5 squared. So that simplifies into x squared minus 2 over 5 squared. So our A is 2 over 5. So now we have it into a form, x squared minus a squared. X squared minus a squared is a secant function. So we know this is going to be a secant function. So we have to first define x. X equals a secant x, secant theta, which is 2 over 5 secant theta. Then we have to take the derivative of this, which becomes 2 over 5. The integral of secant, or the derivative of secant, is secant tangent d theta. And it's got to be greater than 0, so we're going from theta pi over 2. Yeah. All right, so let's look at what we have here. We start with here. So we have x squared minus 2 over 5 squared. Okay, so I'll move my part here. Okay, so we're going to do a squared secant squared minus a squared. So a squared 4 over 25 secant squared theta minus a squared, which is 4 over 25. Since they have both 4 over 25, we can factor those out. So we have secant squared theta minus 1. That's an identity. tangent squared. So then if we take the integral of, the radical of it, x squared minus a squared, and it's square rooted now. So we'll have 2/4 tangent theta, or 2/5, I'm sorry, 2/5. So if we take the square root of it, now we have our radical. So what we have our original equation was dx over 25 x squared minus 4. So this whole bottom part became, we had this. So we have 5 radical x squared minus 4/25, which became what we have here. This is 2/5 squared, which is dx. On the bottom, we have 5 times 2/5 tangent theta. And dx, well, we did that. Dx is here. So that becomes 2/5 secant theta tangent theta d theta. This can go out in front, so it's 1/5. The 2/5s cancel, the tangent cancels, so we have secant theta d theta. This is 1/5. The integral of secant is ln secant theta more is that. It's secant. Okay, there it is. Here's secant. So secant theta is the same thing as 5x/2 plus the tangent part. The tangent part is here. So tangent theta becomes 5 radical x squared minus 2/5 squared over 2. Yeah. So it'd be 5/2 radical x squared minus 4/25 plus c. Yeah, so once we did the transformation to trigonometric functions, We have to remember these conversions because when we go back to this part, we have to go back to the x's because since we started off with x, we have to end up with x. Yeah, this is more of a puzzle than it is a procedural. If you notice, I mean, it's pretty much always the same steps. Where's dx? We did that at the beginning, and we went ahead and converted all these. What we found here was that. And we just substitute. This equals that. The fives cancel. Well, let's see, 2 or 5. The 5 comes out in front. And then tangents cancel. Yeah, so then we have this. Then we go back to our cheat sheet. Integral of secant is ln of secant plus tangent. One over 5 ln secant theta plus tangent theta plus c. Secant theta, go back up here. Tangent theta is here. And there you go. That's pretty much all there is to it. I'm sorry, it sounds like all there is to it. There's a lot of steps involved, and if you mess up one of them, then you're hosed. All right, that does it for today. That's the end of that section. We're end of the 10th week.